Hey everyone, welcome back to Stat 5616. Today we're going to start with our first official lesson. Hopefully you guys have done lesson 0 where you're getting introduced to the class, Canvas, how everything's going to be set up, getting onto Slack so you guys can ask questions and we can work on having great communication through not just today, the entire semester. In today's lecture, I'm going to be just kind of introducing you guys to design of experiments, getting you some terminology, and kind of showing you what our class is going to be about. So we're going to get started. How I'm going to do the notes is through a dot cam, so let's switch on over. So again, today's lecture is going to be focused on discussing the idea of design of experiments and how it's going to relate to observational studies, experimental designs, and we're going to learn some terminology. So first, let's understand the definition of observational studies. Observational studies have factors or treatments of interest that are not manipulated. And so what this means is we don't have impact on manipulated. Perfect. So this means that the experimenter isn't applying or changing aspects of the experiment. In these studies, we can only establish association. Okay, this means we cannot make causal statements. So let's go into an example. Let's say we sample from smoking and non-smoking populations, and we want to be able to compare the lung cancer rate of these two groups. In this example, we don't have control on who smokes and who doesn't, such as age, gender, how often they smoke, and etc. And so if we find a difference in the disease rate between the two groups, we cannot conclude that smoking causes lung cancer. We can't conclude this. Again, we can't conclude that smoking causes lung cancer because we can't control all the factors. We're not controlling anything about this. All we're doing is we're looking at these two populations and we're seeing the rate of lung cancer. And so there can be extraneous factors sometimes also called lurking variables that lead to the inclination of smoking and also increases the lung cancer rate. And so with observational studies, we aren't controlling external factors. And so a lot of the times you probably have heard this, that we can only conclude smoking is associated with lung cancer in this case. Again, observational studies, we can only do association, not causation. And typically, you guys have probably seen some memes out there that pretty much people try to make causation when they can only make association. So hopefully these two memes kind of give you guys a little chuckle today. Now, where we're going is, instead of observational studies, we have a thing called designed experiments. In this case, the factors or treatments of interest are manipulated by the experimenter. And we are able to control factors, and so we can establish causality. But there is one hard part, and there are practical difficulties associated with designed experiments oftentimes. And so, for instance, let's go to example 4, which is how can we design an experiment to establish causality of smoking to lung cancer? So in our first example, we were just watching people that had smoking and non-smoking, and we just observed. And this one, we're going to design it so that we can hopefully make a causal statement. How we're going to do that is by first we select a group of people with the same smoking history. So we want to have our initial groups to be as homogeneous as possible. We don't want maybe 16 and 18-year-olds smoking. We don't want that in general, and trying to compare that to maybe a 50-year-old or 60-year-old. We want to try and create our groups to be as homogeneous as possible or the same. Then we're going to randomly assign each person to be a smoker or a non-smoker. How are we going to do this? One way is we could just toss a coin and say heads gets you a smoker, tails gets you a non-smoker. So we're just kind of randomly. We want to be able to do it randomly, maybe through a random number generator or something like that, so there is no subject or experimental bias. So how we do this? Maybe a coin flip type of procedure. Okay, and so then we assign the treatment of smoker and non-smoker, and that's what we're changing. So each person, are they smoking or not? And if the disease rates are found to be different in the two groups, then we can conclude that smoking causes lung cancer. The practical difficulty in this design of experiment is that it's not ethical to actually make people become smokers, especially if they're trying to quit. So IRB would definitely not approve of this study. There are, in some medicine studies, case-controlled studies, but the main point here I'm trying to get at is if we can't control the other factors, we can't make causal statements. If it's possible, it's always better to do a designed experiment compared to an observational study, because we can start making these causal statements. Okay, and so with design experiments comes a lot of terminology that you will hear. And so to introduce the terminology, I want to first start by having an example that we can come back to. So our example is the Virginia Beach Shrimp Company designed a study to look for the best conditions for the growth of commercially raised shrimp. The VA Shrimp Company looks at two treatment factors: temperature at 25, 30, 35, and the water salinity, so at 10%, 20, 30, and 40. The company raises the shrimps in controlled containers and weighs the individual shrimp after 6 weeks. So the first term, you guys will probably know this, is we call the response is the observed measurements, so which are the subjects to vary. So in this example, where they are, in this example, are individual shrimps, because that's what we're measuring, we're weighing the individual shrimps, are going to be our response. So shrimp weight is our response. Okay. Now, the water temperature and the water salinity are the treatment factors. They're the factors of primary interest and which we're going to control. So our treatment factors are going to be water temperature, and salinity. Okay, these are what we were interested in controlling to see an effect. Now, for our temperature, we had 25, 30, 35. And so the levels of your factors are what we call treatments. And then for the salinity, that's 10%, 20%, 30%, 40%. And so treatment factors are the broad factor of interest, the temperature, the salinity, while the treatments are the actual levels we're looking at. So the degrees of temperature or the percent of saline. Okay, now factors or levels of these factors can either be quantitative or qualitative. So we can have 20, 30, 35 degrees, or we can have cold, warm, hot. In our later examples, we're just going to have cold, warm, hot. Okay. Now, again, today's lesson is all about introducing us to new terminology and some designs that we'll be looking at. And something that's going to be really important are what we call blocking factors. And these are the factors that we identify to account for extraneous experimental errors. So what we try to do is block out additional sources of variability, and in doing this, it's going to help improve our inference and our conclusions. Now again, just like treatment factors and treatments, we have blocking factors and we have blocks, which are the level of the blocking factors. In our current shrimp example, we don't have any blocks, but we will bring blocks up in a couple of examples to help give us an idea, okay? Another thing that is very common is looking at combined treatment factors okay? And these are the factors that you are going to cross to get it. So back to our shrimp example where we had water temperature and saline. If we did the combined treatment factors, and we were just looking at the water condition, it would be combining the temperature and saline. So we would have 25 degrees and 10%, and we would have the different combinations. So in this case, because we have 3 temperatures and we have 4 salinity levels, we'd have a total of 12 treatments. Another term that we may use in this course is the idea of a control treatment. And some of you guys probably have used this in your research. And a control treatment is all about just having a baseline or a benchmark. In medical studies, this is typically seen as the placebo, the sugar pill, where you're giving them nothing. It doesn't have to be just like that. It could be your original or your current treatment, and you want to see how different treatments compare to your baseline or your benchmark. So these are just some terminologies we'll be using throughout this course. I want to introduce them early so that we can continue to work on understanding them. Now, while this terminology is great, the one main question some of you guys might be asking is, what is the objective of all these designs experiments? We talked about observational studies and how we can only make association statements. And then we said design experiments allow us to make causal statements. But what is the objective of design experiments is to understand the effect of the treatments on the response. And so we're applying some treatments. I abbreviated there to try and save some time. We're applying treatments and we want to see how they're affecting it. And so some ways we do this is through a treatment design, which is the protocol for defining and applying treatments. Then we also have subsampling, which is a protocol for measuring a response of the observational unit. Now, this term will come back into play in about a couple minutes, and this term is going to be important. Okay, so treatment design is how we're going to apply our treatment, so that a little bit of randomization is coming in there. Subsampling is going to be the protocol for measuring the response on the observational unit. And then our error control design is the protocol to help us identify and account for systematic variability. Beyond that, due to just the treatment. Okay, so our goal of experimental designs is to figure out the treatment design and understand the effect of the treatments. But we're going to use the error control designs to be able to efficiently and effectively understand the impact of the treatments and to take into account the variability associated with the other factors. And so let's talk about some treatment designs. So now what we're going to do is we're going to briefly discuss these three topics. Let's start with treatment designs. And so some of the topics that designs will be covering are the following. So a one-way classification has just a single treatment factor. This is going to be in lesson 2. We call it a completely randomized design, where, so if we go back to our shrimp example and we ignore water saline and only consider treatments as the temperature, so 20, 30, and 35. Another treatment design is called a factorial treatment design. Treatments are formed by the combos of the levels of all factors. Okay, so what our treatment design for here would be applying all 12 of these treatments. So sometimes in practice, this is very hard to do due to time and resources. And so some people might opt towards a fractional factorial design, which only a fraction of all the level combinations are selected. So maybe you only do this side, or you only do that side, or you only pick those top 4. And so the advantages is you can save resources by studying less combinations. That makes sense. But the harder part is, how do we choose from these 12 the ones that would give us the best or are helpful? And so if you did more studying on design of experiments, you would start to learn which ones will be optimal and stuff like that. So there is a lot of difficulty in choosing which ones, plus there are confounding effects. What I mean by confounding effects is that we want to be able to estimate certain effects uniquely. So we'll get more into confounding effects later on. If you do want to study some more about fractional factorials, we won't cover too much, I believe, in this class about it. Stat 5204G will give more details. Another design that we're going to briefly discuss is nested designs. And this is the level of one treatment factor is nested within the level of another treatment factor. So for instance, we have saline nested in temperature. Temperature 25, we have saline at 10%, 40%. Temperature 30, we have these 2 salines, and 35, we have these 2 salines. So a nested design comes into play when the properties of one level vary depending on the level of another factor it's associated with. So what I mean by that is, let's say, for instance, we're at temperature 25. We can only have saline at 10% and 40% for some given reason. The saline is varying within the temperature. And again, if this doesn't make sense right away, I'm just trying to introduce you guys to some of the terminology. So as we move throughout the class, it will maybe be like, oh yeah, we talked about that previously. Now, an important part of design of experiments is understanding the difference between an experimental unit and an observational unit. Some say that this is probably one of the hardest things in the semester, just getting our heads around these two terminologies. And our homework, I say ours, your homework 1 is focused on trying to identify these two terminologies in various cases. So when you start your experimental design, it's important to figure out what these two are. An experimental unit is the objects to which treatments are applied. Okay, so we have a treatment and we're applying it. That's an experimental unit. An observational unit are the objects from which the responses are measured. Okay, here's a keynote, like big keynote. These are not the responses. Okay, this is not, like, big keyword. And the reason why I'm trying to make this very obvious is because this is where a lot of students mess up the first time when they're learning about these two terminologies. So experimental unit is what we're applying, the object to which the treatment we're applying, and the observational unit is the object from which we're taking a response from. It is not the response. So the best way to understand these two concepts is to just go in through some examples. So let's go through that. So our first example, which is continuing our shrimp example from before, we have set water temperature and saline for an entire container of shrimp, and we will measure the weight of individual shrimps. What is the experimental unit and what is the observational unit? So our EU, which is abbreviation for experimental unit, is going to be the entire container. Okay, because we're setting the temperature and saline for an entire container. Our OU is going to be the individual shrimp. Why? Because we're taking measurements of the weight of the shrimp. It's not the weight, but it's the actual shrimp, because that is what we're getting our response from. Okay? Again, these definitions, important. Okay? Let's go to a couple more examples just to make sure we get our heads around these two concepts. If I can flip the page. So now I modified question 5 just slightly. And so we set the water temperature and saline for the entire container of the shrimp, and we will measure the total weight of these shrimps in each container. And so in this case, our EU, again, is going to be the entire container. And our OU is also going to be the entire container. Why? Because we're measuring the total weight of the shrimp in each container. We're measuring all the shrimp, and so it's in each container, and so our observational unit is the entire container. Okay? If you want, you can pause the video and try these next couple examples to see if you understand EU and OUs as practice. I would recommend it. It's always good to get more practice. Okay, let's go to example 6 now. In studying human diets, 20 people are randomly assigned a particular diet, with 10 people receiving diet 1 and the other 10 receiving diet 2. After 2 months, we measure the weight loss of each person. What are the EUs and OUs? So, in this case, our EU is going to be our 20 people, because we're going to randomly assign a diet to the people. The people are the objects in which we're assigning our treatment of a diet. Our diet is the treatment. We can go A and B, okay? Our OU is also going to be our 20 people, because our response is the weight loss of what object? Our people. So EU and OU. Let's go through another example. In studying the fish diets, 6 tanks of fish are randomly assigned a particular diet, and each tank contains 100 fish. After 4 months, we measure the weight loss of each fish. What are the EUs and OUs? And so here to help demonstrate this, we have 6 tanks, 1, 2, 3, 4, 5, 6, each with 100 fish in it. And we're going to randomly assign diets. Let's say our diets are A and B. So we'll go, this one gets A, that one gets A, that one gets A. And this tank will get B. And so hopefully that demonstrates that we're randomly applying the diets to the tanks, that our EUs are the 6 tanks, and our OUs are going to be the 600 fish, because we are going to measure the weight loss of each fish. Our response is going to be the weight loss. The object from which we're getting the response is the fish. Now, I want to bring up a little bit an example that may be a little bit more trickier / foreshadow what the class is to come. So in example 8, in studying for irrigation in 2 fertilizing methodologies, 24 fields are selected for the study. So we have our 24 fields. It is much harder to change the irrigation method, so fields are assigned to an irrigation method in a block of 600 fields, 6 fields at a time, while fertilizers are assigned to each field individually. The field yield is measured. What are the EUs and OUs? So in this example, this is actually what we're going to call a split plot design. I really don't know why I just put those in quotes. I'm not going to lie. Probably shouldn't have quotes because there's nothing quotey about this. A split plot design. So let's talk about how we're going to set this up. So we have our irrigation methods, and we have 4 of these, and we're going to label them A, B, C, D. Okay? And they are set up in blocks of 6 fields. Luckily, our picture here is already in blocks of 6 fields. So with the irrigation, we're going to randomly apply each method to these 6 fields. So let's say A, B, C, D. So we're going to apply irrigation method D to that, B to these 6, A to that. Now, we also have to assign our fertilizer. So we have our fert, and we have 2 treatments. We'll just call them 1, 2. And now within each of these blocks of 6, we're going to randomly apply the 2 fertilizers. So 1, 2, 2, 1, 2, 1. Again, we can randomly apply it again, and this one, and so forth. We'll just finish this up. Okay, and so let's think about what our EUs and our OUs are. Our EUs, again, are the objects in which we are applying the treatment to. And so in this case, our objects, our first experimental unit is the block of 6 fields, okay, that are getting the irrigation treatment. Our second EU, in a sense, is the 24 fields that are getting the treatment of fertilizer, okay? Now our observational unit, where's my blue pen? Again, is going to be the object in which the responses are measured from. And so here, we're going to be measuring the yield from each field. So our OU is the 24 fields. Okay. Again, you're gonna have more practice of EUs and OUs on your homework assignment, so more practice, the better. Now that we've kind of briefly talked, again, about the treatment design aspect of experimental designs, we're going to talk a little bit about subsampling. Subsampling is, it allows us to see multiple observations in a study. And so, again, the protocol for measuring responses of the observational unit. So hopefully this should make more sense. Often if our OUs and our EUs are equal, the number there is no subsampling. So let's talk about 2 quick examples with and without subsampling. So in our shrimp number 5 modified example, we set the water temperature in the saline for the entire container of shrimp, and our response was the total weight in each container. In this case, we don't have any subsampling because our number of EUs and OUs, they're the exact same. Okay, now if we go back to our fish example in example 7, this one right here, we do have subsampling because our experimental unit is, oh, that's the wrong page. Where'd it go? Here we go, this is yours. That last one was me prior to this lecture. We have 6 experimental units, and our OUs for this one experimental unit has 100. And so we get a lot of measurements, our OUs. We have multiple OUs in this EU. And so our number of subsamples per EU is 100 fish. One way you can also look at subsampling is it's a way of looking at the variability of our measuring. And so what I mean by that is in this case, in this tank, we have 100 fish. If we measured 100 fish, we would get an average weight, and then we can get some variability. It's a good way to look at our measuring, in a sense, measuring our measuring instrument. That's a side note, we'll get to it more, but subsampling is all about the observational units, okay? The third topic with the design of aspects was the error control design. And so this is, again, the protocol to identify and account for systematic variability beyond that due to treatment difference. So the idea of design of experiments is that we want to explain things as well as we can. We want to explain the phenomena that we're looking at. Thus, the idea is that everything is an error. And then we start out by trying to break up the experimental error into what we call systematic variability and unexplained variability. And our goal is to reduce the unexplained variability. This is also background noise. background noise. And this is going to make more powerful inferences. So if we can explain more variability in the systematic, then we're going to have stronger inferences. In simple terms, if we can understand why things are working, we want to be able to put them in our systematic variability. The more we understand, the better our inferences. So again, our goal is to get less unexplained so we get better inferences. So let's go to an example that kind of demonstrates this a little bit more. And we're going to give you guys an example with blocking. So let's say we start with containers with equal weights of shrimp, and we set the water temperature and the salinity for each container of shrimp. Now, we also have two assistants who are going to help take care of half the containers. And assistant A is lazier and tends to give less food to shrimps than assistant B. Our response is going to be the total weight of the shrimp in each container. Okay? So, in this example, we are going to have a blocking factor of the assistants. But let's talk about if we don't, a good way and a better way to design this. So let's say we just have our treatments. Our treatments are going to be cold, warm, hot. For the sake of simplicity, I'm just going to pretend we don't have salinity because it's easy to write cold, warm, and hot. Okay, this is going to be broken up. This is going to be kind of our bad design, and this is going to be our good design. So we can randomly assign hot and cold to our experimental units. So let's say we have hot, hot, cold, warm, warm, cold, okay? And now let's say we give the top three to assistant A and the bottom three to assistant B. There's a problem with this setup because assistant A is going to have two hot and assistant B is going to have two warm treatments. And the issue with this is that we wouldn't be able to break up the association of whether hot water actually gives the shrimp less weight, or if it's because assistant A is lazier and gives them less food. So there's that confounding effect that's happening of, is it because it's hot water, or is it because assistant A gives less food? So a better way to make this design with a blocking factor with our assistants is to say, okay, let's assign these three experimental units to A. Let's assign these three experimental units to B. And now within these three, let's randomly put hot, warm, cold, cold, warm, hot. And so what this is going to do now, and we're going to be able to make a conclusion, this is also called restrictive randomization, is by doing this, we're going to block out the variability between the two assistants. And so now, when we compare, if these three are lower than these three, we can at least assume that it's going to be because assistant A gives them less food. And we can still look at the effect of treatment by putting this blocking. So the point of blocking is we found a factor that could impact the result and we blocked it. So now in our controlled error with blocks, it allows us to incorporate this blocking or the assistance into the systematic variability rather than the unexplained. So let's recap that. So again, our experimental error is broken up into systematic and unexplained variability. When we use blocks, we can take our treatments and our blocks and categorize it as systematic variability. We can understand it. and leave the random variability as the unexplained. Okay, but if a blocking factor exists, such as our assistance that we have here, but it's not incorporated in our designs, then our blocking variability is actually going to be put with the unexplained, and thus giving us less powerful inferences. Okay, and again, if this doesn't all make sense yet, the whole idea of blocking, that's okay. We're going to have, I believe lesson 3 is all about blocking. And so we'll get there. Again, this is just to introduce you guys to some topics, get you thinking in the statistical mindset. So some of the designs that we're going to talk about are a completely randomized design. That's lesson 2, randomized block design, which incorporates a blocking factor. And then we'll also be talking about Latin squares, which incorporate 2 blocking factors. Okay, now, something that's very important to the validity of any inference are 2 terms called replication and randomization. So randomization is when you randomly assign treatments to the EUs. This is going to help us provide an objective approach to treatment assignments. It's going to lead to statistical independence among responses. And more importantly, it's going to average out things that we didn't even think of. And so what I mean by that is, if here is our shrimp example again, where we have our hot, hot, warm, warm, cold, cold, randomly assigned. There's something, maybe, let's say there's a window right here, and it's snowing outside, and the insulation isn't good, and so the cold air seeps through and makes these 2 buckets even colder, and which is going to affect it. But if we are randomly assigned stuff, it's gonna end up averaging out weird things that we don't think of. So randomization is always good. Typically what I would suggest is that even if you think yourself, oh, I just randomly assign that, do some random number generator, which we'll talk about, and there will be a video about after this, so that you have put no bias into your designs. The next thing that's important for statistical inference is replication. Replications are duplicates of treatments assigned to the EUs. Oh, that's an extra one. And so doing this is going to allow us to create inferences. If we only have one replicate, we can't have inference. It's also going to help us assess the unexplained variability. And so what I mean by this is, in this example up here, we have hot and hot. We applied under same conditions, the same treatment. And so any differences among these 2 treatments is background noise. So difference between these 2 would be called background noise, unexplained variability. And the point that we want to be able to do is to see if there's enough difference between this hot container to the warm that is above and beyond the difference that's just between the background noise of the hot treatment. So is there a signal, i.e. difference between these treatments, that is enough beyond what we're seeing just with background noise? And so this is kind of what we're looking at when we compare signal to noise. This is similar to ANOVA, which you should have studied in Stat 5615, and we will be going over ANOVA again in lesson 2 next week. Okay. Also, as a note, in a balanced design, the number of replicates is going to be the number of EUs over the treatments. What balanced design is an equal number of treatments per EU. So in this case, our number of EUs is 6, and our number of treatments is 3, and we have 2, which makes sense. We have 2 hot, 2 warm, 2 cold. Okay? So something we want to be careful about here is subsampling and replication. So subsampling is not replication. Ooh, this printed out a little bit worse, but that's okay. Replications are going to be the duplicate of treatment assignments to EUs, and subsamples are going to be duplicates of OUs, okay? So let's go to an example. Here's an example where we have 3 containers, which we apply our treatment to: cold, warm, hot, cold, warm, hot, and then we have 10 shrimp in each container, okay? Our EU is going to be our container, and our OU are going to be the 30 individual shrimps. Okay, so in here, the number of subsamples is going to be 10 per container. And you can figure this out because we know our OUs are individual shrimps, and in each one we have 10. So we have 10 duplicates of our OU in this EU. Another way is that our number of samples is going to be equal to the number of OUs divided by our number of EUs. Our OUs again is 30 over 10, which makes it 3. Whoa, my goodness, that is not right. Our number of EUs is 3, 10. Got a little excited. Okay. Here, the number of replicates is equal to 1 because we only have 1 experimental unit per treatment. Our treatment is cold, warm, hot. We only have 1 experimental unit, the container, for our 1 treatment of cold, for our treatment of cold. And so 1 replicate, we can't do any inference. But if we were to change this up a little bit, and we now say that we do have replicates, so we have 9 containers, and we're going to apply warm, 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 cold, 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 hot, hot, hot. Randomly assign that, put no thought, just did as random as I could. And so here again, our EUs are our containers. And so what we can see is our number of reps will be 3, because for this treatment of warm, we have 3 experimental units. For this treatment of cold, we have 3 experimental units. And so thus we will have 3 reps. This is also what we would call an example of a balanced design. So again, that's the number, there are equal number of replicates per treatment. An unbalanced design would maybe say if we got rid of that, then warm, the warm treatment only has 2 while the rest have 3. It's not a balanced design anymore. So now I want to talk a little bit about randomization and how we can do this in software. So the rest of the lecture, we're just going to talk about how we can randomize. And this can be done in pretty much any software that has a random number generator. So Excel, Jump, R, Minitab, MATLAB, I could keep going on. But let's just kind of give us a procedural way to do this. And then in the next lecture video, I'll show you how to do it in R and in Jump. So I'm also going to start introducing some notation. So we have T, so little t is going to be treatments, and we have little n, which is going to be the number of replicates per treatment. So our total number of observations is going to be capital N, which is going to be T times N. And I should have prefaced this by saying we're going to have a completely randomized treatment assignments. So little t is our treatment. We're going to have little n replicates, and our total number of observations, also the total number of EUs we have, is capital N. How we got that is T times N. So this is a kind of clunky way of looking at it, but I know sometimes having steps written down help some people, so I'm going to apply these steps in an example. So in our example, we'll have 3 treatments of 3 replicates, very similar to our example 11 that we just had. And so our first thing is we're going to take our EUs and we're going to assign a number to them. So we did that here. I just gave a number to them. Then what we're going to do is we're going to randomly permute 1 through n, and we're going to assign it to K1, K2, Kn. And so what that's going to look like is pretty much I'm taking these number 1 through 9 and I'm shuffling them, and then I have a list. And now what we're going to do is going to assign the first little n treatments to treatment 1, the second to treatment 2, and so on. And so here's our random permutation that I got from software. And what we're going to do is we're going to take these first 3 and we're going to apply cold to them. We're going to take these 3, apply warm. We're going to take these 3 and apply hot. So 4, 8, 9, 4, 8, 9 are going to be hot. Warm is going to be 2, 5, 7. Cold will be 1, 3. Oh, cold, cold, cold. And so this is our random assignments to our EUs for an experiment that's just completely randomized. Now, we've talked a little bit about blocking today, so let's just do an example for blocking. Also, on your homework, you're going to have to do something similar to this. Again, there will be a video for you guys on this. So let's just repeat what we have. We have T treatments. We're going to have little b be our number of blocks. N, little n's are replicates. And then our number of experimental units is capital N, which is equal to B times N times T. And so our question here is, how do we assign treatments to these N with blocks? And so within each block, we're going to have NT experimental units, and then we're just going to apply the previous procedure to the EUs within the block. So let's explain what I mean. Let's say we have 3 treatments again, cold, warm, hot. Now let's say we have 3 blocks, assistant A, B, and C, and we're going to have 1 replicate per treatment block. So here would have been our 9 blocks. I randomly assigned 3 EUs to block 1, block B, and block C. Now I have 1, 2, 3. So block A, I'm going to randomly permute these, and I'm going to assign warm, cold, or hot. Then I'm going to randomly assign these, and I'm going to randomly assign these. So right here, what this is saying, K1, 2, 3, is these right here, oh, wrong color. These right here should be blue, are going to be assigned cold. These will be assigned warm, and these will be assigned hot. And so we can see that in block A, EU3 gets cold. In block A, EU1 is getting warm. And so that's how that goes. Blocking here is also serving as replications, but we'll talk about that a little bit later. And so lesson 1 was solely on getting you guys introduced to DOE, starting to get into that statistical mindset. The real big thing you guys want to get out of today's lectures is the definition of an experimental design, which is the object in which we're applying the treatment to, and observational units, which is the object in which we're getting the measurement from. So with that, you should be able to do your homework. There are also r/jump videos to talk about how to do randomization in those two softwares. You should be able to do your homework now, and see you guys next week.